All right, let's get started. Hello, everyone. Welcome to today's webinar. Thank you so much for listening in. For those of you, let me make sure I'm properly sharing my screen. Yeah. For those of you new to our webinars, audio is provided via the GoToWebinar application over the internet. So please enable your speaker in all places. The application has muted your microphone. So if you have a question, you can use the questions tool at the right side of your screen, again, through the GoToWebinar application. You can use this at any time throughout the webinar. I will try and answer questions as I'm going through. If for some reason I don't get to your questions, we will send out answers to everybody all at once so you can all benefit from those answers. Today we're going to talk about an overview of the safety lifecycle with exSILentia. So we're going to walk through sort of a larger view of each of the tasks that you do in the safety lifecycle and how we would handle that with a fully integrated safety lifecycle tool. This is part 2 of the webinar. So a couple of weeks ago, I went over part 1, which covered the analysis phase of the safety lifecycle. Today, I'm going to talk about design and implementation, and I believe there's going to be a part 3 to talk about operation and maintenance. But as I said, check out part 1. It is on YouTube. It's on exida.com. It was done May 23rd, and it gives a really good overview of the analysis phase, both conceptually, and then we dive into the tool and show it to you. I'm going to do the same today with design and implementation. But first, I should introduce myself. My name is Kate Hildenbrandt. I am product manager at exida. So that means that I'm responsible for strategy, roadmap, and feature definition for our exSILentia software. I'm also focused on providing training and software support to all of our customers. For that reason, I have my email address here, khildenbrandt@exida.com. If you have any questions for me about products or exida at large, please do not hesitate to use that email address and contact me with those questions. Also, a quick overview of exida. I know many of you are familiar with what we do, but we want to highlight that we have 3 different functional groups in the company. We have our enterprise tools. We have tools for functional safety, which is what I'm going over today, but we also have tools for alarm rationalization and cybersecurity. We also have consulting services for all 3. So anything you do in the tool, if you need a little extra help, we have a consultant that can help you through any of the lifecycle tasks. And again, for alarm rationalization and cybersecurity as well. We also do certification for devices used across the industry in your safety instrumented systems, and we do personnel certification. So if you've heard of the CFSC or CFSP program, we also certify personnel. And these work really well, especially from my perspective in the product group. Our consultants do use our tools to do the consulting services, and the certifications help to provide the failure data that we use in our SIL Verification tool, which is something I'm going to talk about in a little bit. We do have offices internationally. I personally am located in Pennsylvania, right outside Philadelphia. But if that's pretty far from you, hopefully you can see an exida office near your location. So let's dive right into a overview of the safety lifecycle. Now, if you caught part 1 of this, we're going to take another look at exactly how the safety lifecycle gives us a method to analyze, implement, and maintain a safety instrumented system. This starts from project scope definition to decommission. And part 1 did focus on analysis. We're going to focus on design and implementation. But it's really important for us to highlight that this is how it looks in the standard. It's sort of almost a checklist of tasks, but it has a clear beginning and an end. And when we actually try and create a work process to address all of these different requirements, we find that it is more of a cycle. So from a data flow perspective, the information needed to complete all of these tasks flow in a cycle. So let's say, for instance, in your PHA, you have a deviation that a challenge to your process parameters that could cause a hazard. So you document your cause, your consequence, and you have your resulting risk. If the risk is high enough, you're going to account for any safeguards in place that are going to help mitigate that risk. Those safeguards become independent protection layers in the LOPA when you're doing your LOPA analysis. And some of them are going to be independent protective functions or safety instrumented functions. They are a safety instrumented function if you find that the risk reduction factor is greater than 10. So in that case, you're going to undergo SIL selection. What is your target safety integrity level for that SIF, or target risk reduction factor? And then you're going to document the requirements for your safety instrumented function in the Safety Requirement Specification. And this is meant as a handoff to the design team to basically say, you need to design this safety instrumented function to meet the safety criteria. So that is a key communication tool between those doing the analysis and those doing the design. Finally, you have to model your safety instrumented function. You do that in SIL Verification. Here you're deciding what your SIF architecture is going to be. You're specifying equipment, and you're setting your proof test strategy. So you have to do functional tests throughout the life of the SIF on the equipment to make sure that it's working, so that if a hazard actually occurs, you know that that piece of equipment will act and respond in a way that takes your process to the safe state. Because a lot of this equipment is sitting and waiting for a hazardous event, sometimes you want to ensure that it actually works and moves the way you need it to in the event of that hazard scenario. When you're deciding on the amount of redundancy you put into the SIF, when you're deciding on the equipment that you're purchasing, and also that proof test and maintenance strategy, you want to take into account how much this is costing. So you want to optimize your SIF design, obviously, to ensure that you're meeting the integrity requirements, but also to make sure that you are coming up with a cost-effective solution. So we also have a life cycle cost estimator that's going to take into account the equipment cost, cost to install, cost to do proof tests, so on and so forth. Once you have completed your conceptual design, you want to write another safety requirement specification for those people who are going to implement this design. So we have what is called a design SRS. This is going to differ from the original SRS because that had intended proof test intervals, intended mission times, intended SIF architecture that might have had to change in order to actually achieve your safety integrity requirements. And so this is meant to communicate what your conceptual design is finalized as, and hand that off to the implementation team. And the reason we don't necessarily go back and update the original SRS is because at times it's a contractual document. So we don't want to mess with it. We don't want to rewrite work that other people have done. But now we have, in the next step, a design SRS that we can hand off to the implementation team. Once you're in operation and maintenance, you have to actually perform the proof test. So we have a proof test generator. Every piece of equipment has an associated proof test from the safety manual. So if you're pulling from exida's database, and we'll talk about this a little bit more, we have associated proof test steps and a proof test coverage, which is an indication of the amount of failures, dangerous failures, that are revealed during a proof test. If you're doing your proof test according to the steps given, then it has an associated proof test coverage, which is an important part of the calculation. So we're able to generate that proof test for you. For your entire safety instrumented system, you have one proof test report, or for each SIF. And then obviously, you want to go out and record those proof tests. You want to record the results. Are they passing? Are they failing? And you can do that in the life event recorder, which we call SILstat. Along with recording the proof test, you can do routine maintenance. You can record any device failures, and you can record demands on your process. And all of this data over a number of operating hours can give you not only validate your analysis and design, but give you data that you can use in the future for perhaps a greenfield project where you're putting in a similar process. So that's what SILstat does. Another thing to highlight is you want to do alarm rationalization to make sure that your alarms are set up in a way that the operator can effectively respond to them. So we have a tool called SIL Alarm that would help you to walk through that alarm rationalization process. Obviously, some alarms with operator response are accounted for in our PHA and LOPA. And so you want to make sure that if you've taken credit for them, that the operator actually has time to respond to that alarm, or else it's not useful and you're going to have that layer of protection fail. So alarm rationalization, very important, and we do have a tool called SIL Alarm for that as well. So you can see how it's a cycle. The data flows from one task to the next, and we aim to have our tool facilitate that data flow. If we go back and break this up into pieces, we know we have the analysis, design, and operation and maintenance phase. And as I said in the last webinar, we went over PHA, LOPA, SIL selection, and SRS. This time, we're focusing on, as the life cycle itself says, design and engineering of the safety instrument and system, design and development of other means of risk reduction, and then installation, commissioning, and validation. Well, how do we sum that up? You need to do your conceptual design in SIL verification, need to communicate it in the design SRS, and some of that implementation is configuration of the safety logic. If we look a little deeper, obviously SIF conceptual design and SIL verification, you're modeling your SIF, choosing how much redundancy you need, choosing the equipment you're going to implement, and choosing your proof test strategy. Then you're going to document all the SIF requirements for implementation in your design SRS. Now that you know a lot that you need for the logic configuration of your safety PLC, you can do that PLC programming. And then once it's time to implement, you need the proof tests. So you want to define those functional tests for your SIF devices that you can use throughout the life of the plant to ensure that those devices are working and can respond effectively to a hazard and bring your process to the safe state. Well, how exactly can our tool address all of this? And as you can see, just like the analysis phase of the life cycle, it's a lot to do, and having a streamlined work process and a tool to aid that work process can be very, very helpful. So we're going to walk through exactly how we would handle this in the tool. And one of the major components of your conceptual SIF design is knowing how likely it is that your devices in your SIF would fail. So you need a lot of data. You need data for your failure rates, your useful life, your proof test coverage, things like that. So exSILentia has an embedded failure database. We call it our Safety Equipment Reliability Handbook. And this provides data for thousands of devices used industry-wide, as well as generic data. So you can see on the left-hand side, we have a data sheet for generic air-operated ball valve, and this is just a portion of the data that comes along with this device. Now within exSILentia, you can actually simply choose this from a drop-down list, and it's going to autofill the data into the tool and do the calculation automatically. But it's nice to take a look at the data and understand where it's coming from. This data source is exida comprehensive analysis. We do FMEDAs to certify equipment, and we also take into account any field failure data. So if I use a highlighter, you can see here we have a response time, we have the architecture type, and then for this ball valve, we have a couple different options. This is the clean service set of data. We also have a severe service set of data. And that basically means, are you using the device in an application that it was manufactured for, or are you using it in an application that maybe it wasn't manufactured for? And that sort of information would be in your safety manual. If you are, we have options for close on trip and open on trip. For close on trip, we have full stroke and tight shutoff failure rates. And then for each of those, we have normal and PVST failure rates. We have that for tight shutoff and open on trip as well. And you can see here, each of the failure rates are broken into dangerous detected, dangerous undetected, safe detected, safe undetected. You also have the useful life here in years. So the useful life for this device is 10 years. So this is really good information. Like I said, when you're using it within our tool, it's embedded. So you're just choosing the piece of equipment and indicating how it'll be used in the application, and it's going to pull in the correct failure rates. The next step is going to be to model your SIF. And here I have a screenshot of silver, and we're focusing in this screenshot on the sensor part. So you can see on the left-hand side, we have the sensor part expanded. In this case, we have one sensor group and one sensor leg. So here you see the vote between groups is 1 out of 1, just one group. The vote between legs is 1 out of 1, just one leg. Here you can put in your mean repair time, and this is the time it takes to install and start up, procure, install, and start up your plant after replacing a piece of equipment. Then we have the proof test strategy. So you're going to put in your proof test interval, which is the time between proof tests, your proof test coverage, which indicates how many dangerous failures are being revealed during your proof test. And then you can indicate, is it performed online? If so, is there alternative protection? And what's the duration of that test? So that's all going to affect your calculation. We have an option here for another test, and we've labeled the application level diagnostic test, which you can enable if you have such thing. Here you can put in the interval of that test, the duration, the coverage, and indicate if it's initiated automatically. Once you've defined all of your testing strategy for the sensor, you can start to specify the equipment. You can give it a name and a description. You want to indicate the measurement type, in this case it's pressure. The trip setting, is it high or low? If there's a fault in the transmitter, is the signal driven under range or over range? You can indicate that here. And then, do you have any external comparison? And what is the comparison coverage? If your sensor is an analog device, we also have PLC detection configuration options. So can your PLC detect out of range signals? Do you have a transmitter fault filter? So is there a delay before trip, or do you trip on transmitter fault? And then finally, you'll see there's 3 different device types that you can specify for your sensor. We have the process connection, and here we just have clean service. We have the sensor itself and an input interface. Here you're able to choose from the failure rate database. You're able to put in a user-defined device, or you can link to a device that's already been defined, either from the database or user-defined. You can, after you've chosen your device, come here and click the proof test coverage calculator, and that's going to give you the proof test coverage from the database associated with the device. You can also input the proof test coverage yourself. So if you're looking at the steps and you're saying, oh my gosh, we do more than what this proof test is outlined, we know exactly what the additional failures are that could be revealed, and so we can up that proof test coverage. So that's how you would specify the sensor. You can go on to specify the logic solver, and here again, you can select a logic solver straight from the exida database. You can also put together a user-defined logic solver yourself. We do have options for an advanced logic solver versus a simple logic solver. So that's pretty flexible. Here I just chose a generic SIL 3 certified PLC. Again, you can specify your proof test strategy on this side. You can input the interval, the coverage, is it performed online, so on and so forth. You also have an application test here as well in case you're performing another proof test or functional test on your logic solver. Finally, you'll notice that Silver is keeping track of the different modules in the logic solver. So you have your main processor, your power supply, and your analog in, digital out channels. So here you can see the sensor and the final element has already been modeled in this case, so you can see which modules they land on. And we have options that dictate that in exSILentia as well. Finally, you're going to specify your final element, and this works a lot like the sensor. So the first thing you're going to do is pick how many groups. So in this case, we just have one group, and how many legs. So we have one leg, voted 1 out of 1. You're going to put in your mean repair time for the final element and set your proof test strategy just like you did for the sensor. We have the option for partial valve stroke testing here, so you can add that if applicable. And then you can specify your equipment. So you have the name, description, you have a few leg options. Is this valve open on trip? Is tight shutoff required if it's closed on trip? And is this valve in severe service, which again just means any application that the valve might not specifically be manufactured for. And again, that would be indicated in the safety manual, or the manufacturer could let you know. In this case, if we're modeling a remote actuated valve, we have a few devices we can specify here. You can have an output interface. Then you're going to have a final element interface. So this would be like a solenoid, your pneumatic element, and then you can specify a new actuator and valve separately, or an actuator valve combo. As you start to implement some of these, you'll see some of the options disappearing. So you're only going to be able to put one valve in per leg, things like that, which is why it's grayed out. If you are not modeling a remote actuated valve, we do have another option, and I can show you that in the tool. This is anything that could be a final element that's not a remote actuated valve. So we do have that option as well. Finally, when your SIL verification is complete, you have your results. You can see here we have the requirement listed, and then our result, the achieved SIL and risk reduction factor. For each part of the SIF, the sensor, logic solver, and final element, we do have the risk reduction factor that's calculated, the PFD average, the mean time to fail spurious, your SIL according to PFD average, your SIL according to architectural constraints, and your SIL according to systematic capability. We also have the response time, and then we have pie charts that are showing the contribution of each SIF part to the PFD average and to the mean time to fail spurious. We also have PFD charts, which I can show you when we open the tool. So those are your results. It's a lot of information. You'll see that the SIL according to systematic capability is marked as not applicable, and that is an option we have where we're assuming that you've either chosen certified devices or done your proven and use justification outside the tool. You can also do that inside the tool, and you can pick certified devices from the failure database. They're in bold, very easy to find. But if you find that you'd rather document that outside of the tool, you can choose to do that, and this will simply show as not applicable. Once you're done with your conceptual SIF design, we do have the design requirement specification, and this is going to address the requirements outlined in the standard that you have to communicate to your implementation team about your safety instrumented system. So on the right-hand side, we have general SIF requirements, and this is meant to be a bit of a time saver. If you know these requirements are consistent across your safety instrumented system, you can fill them out here, and then using these buttons, you can apply them to all SIFs or one SIF at a time. So this is meant to save some time, make sure you're not filling out the same thing over and over again. Then on the left-hand side, you have your SIF-specific information. You have the name, description, analyst, analysis date, and then for each part of the SIF, you have specific requirements that you would need to communicate. So here you have the process connection information, diagnostics, any startup or restart requirements, any interfaces, environmental extremes, and then we jump into what are your maintenance bypasses, what's your maintenance override requirements, things like that, voting degradation scheme, so on and so forth. So you can fill all of these out, and obviously it goes on to address the logic solver and final element as well. This is a nice consistent way to make sure you're addressing all of the requirements. It almost acts like a checklist, and obviously along with Silver are going to, the information in Silver and the information in here are going to help to generate a really useful report that's obviously consistent every time that you hand it off. So that is good information and a nice consistent report. And I can show you that when we open the tool. The other thing I want to highlight is that Silver and the Design SRS together have addressed a lot of the information that you would need to define when you're configuring your safety logic solver. So for your sensor conceptual design, you already know the number of input channels, the voting, if you have high or low trip, if you have any out of range detection needs, if you have a trip delay, what is the action upon transmitter fault detection? What are your tags? What's the range, the trip point, and the unit of measure? All of that is already defined within Silver. For the final element, obviously we know the number of output channels needed, the tag, and the action for the final element. And then the Design SRS addresses the maintenance overrides, bypass management, your startup overrides, your trip delay time, any auxiliary inputs or outputs, and your reset options. So all of this information is already in exSILentia once you're finished with your conceptual design and Design SRS. So we've created a tool so that you can use this to automatically configure your safety logic. And as you can see in this simple example, we have the input, your voting block, your CEM block, and then your output block. So all of this was automatically generated from exSILentia using the information in Silver and Design SRS. So that's a time saver. It should cut down on the rework that you have to do. We find a lot of people are doing the SIL verification and the logic configuration simultaneously. So if anything changes on one end, you have to go back and change it on the other end. And if they're being done simultaneously, this can be hard and you might end up doing a lot of rework. So by being able to leverage the information in exSILentia to get a lot of this done, you're going to save time. Finally, we have our proof test generator. And again, every piece of equipment that you choose from our failure database has a specific set of proof test steps that it's using to determine the proof test coverage using that proof test coverage calculator that I showed you in Silver. So we have a report we generate, gives you the tag, the proof test interval, that coverage, and then the steps that you would have to follow to make sure that coverage is achieved and that you're revealing those failures during the functional test. One thing I mentioned earlier is that if you find that you're actually doing more in your proof test than is shown here, then you can overwrite that proof test coverage and actually take more credit for your proof test in your calculation. But this is handy in that you have to make sure you're at least doing these steps. So we do have that proof test generator. So with that, we have a practical example that I will use to show you exactly how we do this within exSILentia, and I'll open up the tool to show you that. We went over this example in a lot of detail before we went over the analysis phase of the life cycle. This is essentially a batch reactor. And in this reactor, we have two feeds. It's a sample, so it's feed A and feed B. And feed B is has the reactant in it. We have obviously an agitator. We have a jacket on the reactor filled with water to regulate the temperature in the reactor. And obviously we have a pump that goes to storage. We do have a pressure control here where if the pressure gets too high in the reactor, we open this control valve and vent to an incinerator. You can also see we have a rupture disk. If the pressure gets even higher and something else happens, that rupture disk would lift. But you also notice we have a number of interlocks. So one thing I want to focus on, the scenario that we focused on last time, is what if the pressure gets too high in the reactor? And the only way this would happen is if this control valve failed, meaning that we can't vent to the incinerator. In that case, we have another pressure transmitter on the reactor. And if this senses high pressure, it's going to enact this interlock 3. Now, interlock 3 does a couple things. It closes the valve here of feed B, which is going to slow down that exothermic reaction. It opens the valve here that lets in chilled water to the reactor jacket. And it closes the valve that lets hot water into the reactor jacket. So again, this is going to help to lower the pressure. But the real action that helps bring the process to the safe state is opening this XV500. This is a valve on an outlet line that leads to a quench tank. And what this quench tank is doing is receiving all of the reactor contents. It's 4 times the volume of the reactor, and it's going to mitigate that hazard so that the high pressure doesn't cause a vessel rupture or loss of usable product or anything like that. Again, if this fails, so we have normal operating pressure is 10 psig. Your high pressure alarm goes off at 15 psig. You assume a operator will try and deal with the issue before anything else has to happen. You also have a high pressure alarm at 20 psig, which is when the interlock 3 happens. So that's going to be your safety instrument and function. Then at 60 psig, we have that rupture disk lifting. So obviously we want to avoid that. We don't necessarily want to vent to air depending on what these chemicals are. We don't want to lose any product, but we have to do that at some point. So this is the example that we used in analysis. Obviously at this point, I'm going to start with design, which means starting with SIL verification. So I'm going to model this very simple SIF in silver and go from there. So let me open exSILentia. So when you first open exSILentia, it opens up to the dashboard, and in part 1 of the webinar, I went through everything that the dashboard does. So we went through the project information, project configuration, risk configuration, all of the team member report, export data. I went through the libraries and the databases. You can see up top we have the different modules as tabs. So we went through the PHA, the LOPA, the SIL selection, and the SRS. One thing I want to point out before jumping into Silver is that the failure rate database has a viewer right here. And you can see all of the devices that are in the failure rate database from the dashboard. So if I want to find that same generic valve that I had shown you in the slides, I can view it right here. So in this case, you can see the data sheet, and this is exactly what you saw in the slides. One thing I want to note here is that these are the failure rates for clean service. We have another set of failure rates for severe service. So it's obviously a more extensive data sheet than I was able to show. But this is pretty cool. When you're choosing the equipment from Silver, you are just selecting it. You can actually view this from within the module as well, but it's nice to come in here and see the data firsthand as needed. I'm going to close this, and then I'm going to jump into Silver. I do have a SIF modeled here already, but I have found that it's really more helpful to walk you through the modeling of this SIF. So I'm going to hit this new SIF button. We're going to give it a name. We're going to give it a tag, so on and so forth. So a lot of the information up top here, everything from SIF name to units, is just reference. So I'm going to take some time to fill that out. This is a high pressure protection SIF. And it is measuring high pressure on reactor A. And then dumping contents into quench tank. Yep. The tag, we can give it a BCR SIF 501. You can set an analyst from the team members. I'm going to choose myself, and the analysis date defaults to today, whatever day that you're doing this, but you can also come in and change the analysis date if needed. You can put any comments in the comment field. The references are linking to the library, so you can put any references you want in the library, any P&IDs, any equipment drawings, anything like that. You can actually link them to the library so that you can view them from exSILentia. I'm sorry, you can attach them or link them. So you can put in a link to a SharePoint, anything like that. Here I can just, we have a few defaults, so I have the standard in here, but it would be much more helpful to put a P&ID sheet or an equipment drawing or anything you'd like. In this case, we already have a unit defined, and it is batch reactor, so I can say, yes, that is our unit. So from here on out, the rest of the selections here are actually going to potentially affect my calculation. The first thing I have to do is choose my basis for architectural constraints. My options here are to use the IEC 61508 tables or the IEC 61511 tables. If you're not sure what goes into or how that basis affects your calculation, you can ask us. It is in our SIL Verification course, the explanation of how this could affect your results. And obviously it's in the standards themselves, but you can make that selection here. Also, the selection to consider SIL capability. I don't know if you remember in the results when this gave us the result not applicable, and that's because this was unchecked, meaning we assume we're not going to consider SIL capability within the tool. It obviously has to be considered. So your device either needs to be certified or you have to do a proven in use justification. You can do that proven in use justification within the tool, but if you have a work process for that and you prefer to do it elsewhere, you can simply uncheck this box. And I am going to keep it unchecked because we're going to use some generic equipment in this example. Then you can specify your mission time. So your mission time is the time before you have to replace and refurbish every piece of the SIF in your safety instrumented system. For this SIF specifically. So you would set this parameter per SIF. You can also set it per group if you find that the useful life of your sensor, let's say, is much less than the mission time that was set. But this essentially is going to affect your calculation because your probability of failure is increasing over time. When we take that average, it's averaged over the mission time. So if you are replacing or refurbishing all your equipment after 10 years, you might have a lower PFD average than if you're doing it after 20 years. So that's going to affect your calculation and obviously your operational strategy as well. You also want to enter your as designed startup time. So when you're starting up your plant, how much time does that take? And then select your demand mode. So the options are continuous, high, low, and then you can actually choose to calculate based on demand rate. We're going to stick with low since most of the applications we're dealing with are low demand applications. Finally, there's a option here to have your I/O channels for the SIF on separate modules in your safety PLC. If you uncheck it, then they are going to be on the same module. So you'll have your analog in, digital out, whatever you specifically are modeling on the same module. If you'd rather have them on different modules so that if one fails and the other doesn't, you can check this checkbox, and we'll see how that affects the calculation in a little bit. So if I come over to the navigation tree and expand it, I can begin to model my sensor. And here you see the large Add Group button. I can link a group that is already defined. If I want to link from something from the last SIF, I can do that. But I'm simply going to add a group. Here I can determine voting for the group. In this case, it's just one group, so we're going to stick with 1 out of 1. The name here for my sensor group can be high pressure measurement on reactor A. Ooh, or I should just say pressure measurement. And then I'm not going to fill out a description. I don't want to make this a typing exercise, but you can obviously use this field for a description. I can set the voting here. And again, if you remember, this is just a single pressure transmitter on our reactor. So I'm going to leave it as 1 out of 1, and I'm going to add a leg to match. So now you can see my sensor leg has been added. I can set a mean repair time, and I can set a group mission time. So let's say, like we said earlier, that the pressure transmitter has a useful life of 10 years instead of 15. So I can have the calculation account for that. Then I can set my proof testing strategy. So let's say that I'm doing this proof test every 6 months. You can set that there. I can input a proof test coverage. However, I'm going to elect to choose equipment from the database and then use the proof test coverage calculator to determine my proof test coverage for me. I can indicate here if it's performed online. If so, do I have alternative protection, and what is the duration of the test? However, I'm going to assume it's done offline. And you can enable another test, enter an interval, a duration, a coverage, and indicate if it's initiated automatically. In this case, I'm going to leave that go as well. So now I'm here at my sensor leg, and I can name it. I believe it was PT501. And I could give it a description. I want to then choose a measurement type. So we know that this is a pressure measurement. We also have options for fire gas, proximity, flow, temperature, level, and other. In this case, we're going to stick with pressure. The trip setting is high. And I want if there is a fault in the transmitter, I want the transmitter to drive the signal under range. You can also choose over range. So now I can choose my equipment. You can see these large buttons here, new process connection, new sensor, new input interface, are going to open up the SCRH. And just like before, you can take a look at the data sheets from the SCRH if you would like. In this case, I'm actually going to choose the clean service option. So this means that I have an impulse line and I don't expect it to plug ever. So I can add that device right here. Then I'm going to add a sensor. I have a filter on here, so I'm going to go in and say, you know what, I know I want to use a generic sensor. We like to do this when we're demoing, so we're not choosing any favorites among the manufacturers of the devices. So I can choose that right here. And because it's an analog device, I have a few more options. I have an option for external comparison. So do I have another sensor that I'm comparing this with on a different logic solver? And I can basically reveal some failures by comparing with another pressure transmitter. I'm going to leave that unchecked, but you can then give the coverage for the external comparison. I have some PLC detection configurations. So can my PLC detect out of range signals? I'm going to say yes. Do I have a transmitter fault filter, or am I tripping on transmitter fault? I'm going to leave those go. And now that I've chosen my equipment, I can hit the proof test coverage calculator. And as you can see, it's taking into account the coverages for both devices based on their associated proof test. So I'm going to apply that. You can see I have put my sensor here. I have my voting up here, and I'm all done with the sensor. So now I want to choose a logic solver. And again, I can click the exit a database button and choose one here. I prefer to stick with generic. So I am going to type in generic and select the SIL 3 certified PLC. In this case, you can see I can set a proof test interval. Let's say that I proof test this guy every 2 years. I can set a proof test coverage, and because I've already selected my device, I can do this here. I can indicate if it's performed online, alternative protection, and the proof test duration. If I expand the tree here, you can see my inputs for both. And for the logic solver, you can see that I have module 3 as has the channel for analog in from my pressure transmitter. So it's already starting to basically build the SIF with the logic solver. So that's it for that. Moving along to final element, I can add a group, and this is a lot like the sensor part. It is one valve that I'm opening to dump the reactor contents into the quench tank. So this is valve on reactor outlet, and I believe it was XV500. And here we have a few other options. As I said, if I'm doing, if I'm working with a remote actuated valve, then you can put in an output interface, a final element interface, a pneumatic element, and then you can specify an actuator and valve separately or an actuator valve combo. If I'm not working with a remote actuated valve, there are options under the label other. Essentially, you could have an alarm bell siren, electric horn, indicator lamp. You can have a generic MCC, motor operated ball valve, motor speed drive interrupt, motor starter, or a relay. So these are probably not used as often as our remote actuated valves, but they are options here. So if you're doing other, you could have an output interface and then a new other. In this case, we are working with a remote actuated valve. So I'm going to jump in and define a final element interface. And in this case, we'll use a 3-way solenoid and apply it. And I'm going to go with an actuator valve combo. So we can use this air-operated ball valve and add that. We know our valve opens on trip because we want to dump the reactor contents to the quench tank. So obviously tight shutoff is not required, and we're going to say this isn't severe service. This is clean service. You can see that when I chose my equipment, some of the options were grayed out, and this is because, you know, for each leg you want to have one final element. We can continue to add interfaces or pneumatic elements, but we can't add a motor starter on top of this. So you can see that some of your options are grayed out. Finally, now that I've chosen my equipment, I'm going to hit the proof test coverage calculator and apply the coverage that is suggested by the database. In this case, it has automatically calculated for me. One thing I want to point out, a lot of people ask if you're starting with silver, your requirements aren't filled out. Obviously, if you've done your analysis all the way through, they would be filled out, but because I created just a new SIF, those requirements are not. So I can actually view the information for the SIF here, and a lot of this would be filled out if I had taken it from the PHA all the way through. But I can fill in my requirements. So let's say that my requirement is 20 and that's SIL 1, and that'll show up here at the top. So obviously I have not achieved my requirement. So what do I do about that? Well, I can come in and I can adjust the proof test intervals. So let's say I want to do this every 6 months as well. Calculate, and I know that I need my PFD average to increase or decrease, so I can look at this pie chart that shows the PFD average contribution and see that my final element is basically the one limiting my results here. So I can come in here and add redundancy. So let's say it's actually 2 out of 3. And it's adding 2 more final element legs. They are identical, so I could hit this is diverse button and specify diverse legs, but in this case it is assuming that my same valve is being used. And as you can see, this results in me achieving my risk reduction factor and my achieved SIL. So these pie charts are useful in that way. And one thing I want to point out is the PFD charts show exactly how the calculation is working. So in this case, this is my PFD chart for the entire SIF. And you can see that the probability of failure increases over time. And then at each proof test, it's decreasing. And so from 0 years to 15 years, which is our mission time, you have an average, and that is shown with a dotted line. You can also see the PFD chart for each SIF part. So if you remember, we set a group mission time for the sensor, and here you can see that's 10 years. So this is essentially going all the way down to 0 and restarting at 10 years. So that's going to lower the PFD average. And then we have the same for the logic solver and the final element. So that's another nice way to look at your results. Now, let's say our conceptual design for this specific SIF is complete, and I want to communicate my design to the implementation team. So we're going to move over to the design SRS. In this case, I'm going to use my previous SIF as an example, and it's very similar, simple SIF, but it's all filled out here. The design SRS is a template, so a lot of this information has to be input by the user. Now, it is also pulling from Silver for much of its information, so it's not as extensive as the SRS for analysis that I showed in the last webinar. Obviously, you want to have the name, description, analyst, analysis date right at the top for each SIF. On the right-hand side, we have the generic SIF requirements. So here you can fill out the requirements if things are consistent across your safety instrumented system. You can make those selections here and then use these buttons to apply it to all of your SIFs or one SIF at a time. Once that information is in here, you can come in and change it as needed, and I have already changed some of it, and that's not going to affect the generic SIF requirements. This should be used as a time saver. Obviously, we want to keep you from having to put in the same information over and over again. But here you see some of the sensor requirements. You can see the maintenance bypass information, any maintenance override information, your trip delay time, so on and so forth. What is your startup trigger? What are your legs? Is there a P&ID number you can link from the references in the library? What's your model data sheet? Do you have comparison tag, maintenance override? And then in here you can put in auxiliary legs, auxiliary parameters, and you can link a shutdown level from the shutdown hierarchy. For the logic solver, you can put in common cause sources, and then in here put in a lot of the requirements that we had for the logic solver. So diagnostics, unsafe process conditions, process states, startup and restart requirements, any interfaces, what are the environmental extremes, other special requirements, survivability. And then the final element, you have the same requirements. And then for the leg, you're putting in the name, description, logic solver connection, P&ID, all of that. And here again, you can put in auxiliary output legs and auxiliary output parameters. So all of this is going to allow you to generate a consistent design SRS report. I'm going to open this, and it's going to generate in Microsoft Word. And it comes with a nice consistent template. So as I scroll through here, we do have a purpose and scope. We have some general SIF requirements, so that was the right-hand side. So you can say, you know, generally for a safety instrumented system, these are the requirements. And then it has a SIF list, so both of your SIFs are listed here. Obviously, in a real project, you're going to have an extensive list of SIFs. Then your SIF specific requirements. And you can see that the report actually looks a lot like the module. It kind of mimics the module, so a lot of the information is going to be easy to find. It's going to be easy to find for the people who are entering the requirements into the module, but it's also easy to find for those who are receiving it. It's nice to have a consistent report so you know where the information is, and that's what this achieves. So you can see there's a specific section for the sensor group, the logic solver, and the final element group. This is just one SIF. It goes up to page 15 already. So this can become a long requirement document in a real project, and it's really nice for it to be consistent and streamlined. So that's the design SRS. I also want to show for the proof test report. You can come in here and there's a few options. Do you want to list by SIF tag or SIF name? Do you want to include all SIFs or just selected SIFs? And then again, you can generate this in Microsoft Word. And in this case, I used a lot of generic equipment. So you can see here the pressure transmitter, it shows the tag, it shows the proof test interval, the proof test coverage that was used in the calculation, and all the steps. There's 10 steps here that are going to ensure that that coverage is valid. So you can do this proof test as is, you can add to it, but you want to make sure you're doing these 10 steps to achieve that 90% coverage. And so this is going to basically spit out all of the proof tests that are associated with the devices that you have in your safety instrumented system. And again, you can choose to do this one SIF at a time or for all SIFs. We do have a cost module, so this is going to allow you to take into account the cost of your conceptual design. Part of that is obviously the equipment that you've chosen. You can come in here and put in numbers. These are pretty much just dummy numbers, but you can come in here and put in numbers for each piece of equipment. Obviously, based on how you modeled your SIF, you have a quantity. You can set a reserve level, anything you like. And then you can set tasks. So we know that you're going to have to go through analysis, design, implementation. Some operation and maintenance activities are pretty important to account for. So you know you have to do proof tests for your SIF, but how often are you doing them? Who is doing them? What is their hourly rate? So you have a labor cost, and then what's the material cost of doing those proof tests? And obviously the number of proof tests that you've indicated in your SIL verification is taken into account. You might also have routine maintenance for those devices. This also takes into account the spurious trips. So we have calculated the mean time to fail spurious. In that case, how many events do you have a year and how much is that costing? Things like this are important to take into account when you're doing your conceptual design, and it's going to result in an equipment total, a total SIF cost over the plant life, net present value, and all of that. So you can use this to optimize your conceptual design based on your SIF architecture, your proof test strategy. We also have a cost-benefit analysis that allows you to basically see how much it would cost to not implement the SIF. Sometimes we need to prove or justify putting in a safety instrument and function. And what we need to realize is that at times the hazard is much more expensive than the implementation and maintenance of the safety function. So we do have a tool here based on your LOPA. What are the initiating events? What's the probability of failure of the IPLs that precede the SIF? And what would it actually cost to not put that SIF into the process? So that is the lifecycle cost estimator. It's really flexible and allows you to, I could show you what it looks like blank, but it's pretty flexible and allows you to come in here and put in any of the tasks that you're doing, obviously account for that equipment cost, and make sure that you're obviously meeting your safety integrity requirements in Silver, but also doing it in a cost-effective manner. And the last thing I want to highlight is the SysLogic module. So we have this functionality right now for Delta V, and you can come in here and it is using the information in Silver and in the design SRS to automatically configure your safety logic. So there's not much to the specific module. You can set the maximum SIFs per module. You can include input blocks within composite blocks and generate your shutdown logic. You can create your composite blocks here, set your voter degradation, any user-defined engineering units. And then you can decide if you want to create the FHX file to include all SIFs or just selected SIFs, and if you want it to be in separate files or one file. And then you simply hit this generate FHX files. And this is going to actually output a file that you can save. You can bring it into your Delta V environment, import it in, and open it in Control Studio. And that's where we got that image I showed you in the slide that shows your inputs, your voting, your CM block, and your outputs. This is a very powerful tool, and it allows you to save a lot of time when it comes to configuring the safety logic. It allows your PLC programmers to focus on more, let's say, complicated cases. So in this case, we have a very simple SIF, and you're leveraging that information to automatically configure the safety logic. So that, in a nutshell, is how exSILentia would handle design and implementation. I'm going to go back to the slides. And if you want to know more, we're obviously on Twitter, Facebook, LinkedIn. We are going to do a part 3. So we didn't go over operation and maintenance. I'm not exactly sure when that's scheduled for, but if you're interested in finding out, we can contact you when it's happening. And that's going to show you how what the safety lifecycle tasks us to do for the operation and maintenance phase and how we handle that in exSILentia. If you have suggestions for another webinar topic, please send it to us. We really want these to be useful for you, helpful, educational. So send your ideas to academy@exida.com. And we obviously have our course schedule. This is a screenshot of the North American courses that are coming up this summer. We have FSC 100 in July in Chicago, and then in late July in Calgary. We have a few classes coming up in Sellersville, which is where I'm located. So we have IEC 62443 Cybersecurity for Integrators and Solution Providers, and that's in August. We also have FSC 244, which is SIL Verification with exSILentia, which takes a nice deep dive into SIL Verification, obviously using Silver, but also the methodology behind the calculation. So you can understand a lot of the parameters we went over today in depth. We have FSC again FSC 100 again in September in Anchorage. So this is just North America. I urge you, if you're interested in training, to go to our website. We offer obviously open enrollment like I'm showing here, but also online self-paced training for some of these courses. So that's really helpful. And that wraps it up. So this was our overview of the Safety Lifecycle Part 2. The Part 1 is on YouTube or exida.com. Part 3 is up and coming. And I just want to thank you again for joining me today. We're going to send you any answers to the question you have via email along with a copy of the slides. All right. Have a great day and take care.